Welcome to a deep dive into something absolutely incredible. A truly groundbreaking discovery in astrophysics. We're talking neutrinos, these almost invisible particles that are so hard to detect. Imagine something so small that it could just pass through entire planets like a phantom. That's a neutrino.
And what's really caught the attention of, well, everyone really, is the detection of the highest energy neutrino ever recorded. This isn't just a small step forward. No, it's a giant leap in our understanding of the universe and the forces out there.
It's kind of like finding a message in a bottle,
Hmm.
from a distant galaxy, except the message is this tiny particle carrying a crazy amount of energy.
Yeah, that's a great way to put it. To try to understand the scale here, this neutrino has an energy of 220 PeV, which is, well, orders of magnitude higher than anything we can create, even with our best particle accelerators.
Wow.
It's like, I don't know, comparing a firecracker to a supernova.
So how did we even catch this thing, this cosmic messenger?
That's where KM3NET comes in. It's an incredible underwater telescope situated deep in the Mediterranean Sea. Imagine like a gigantic array of sensitive sensors spread across a cubic kilometer of ocean.
It sounds like science fiction.
It's just constantly watching for the faintest traces of these neutrinos.
An underwater telescope hunting for ghost particles. You mentioned that KM3NET has two parts, right? RCA and ORCA. Why do we need two?
Well, they each have a different focus. RCA, which stands for Astroparticle Research with Cosmics in the Abyss, is designed to detect these high-energy neutrinos coming from deep space, supermassive black holes, exploding stars, things that are so powerful they send these particles across the entire universe.
So RCA is our deep space neutrino hunter. What about ORCA?
ORCA, that's Oscillation Research with Cosmics in the Abyss, is positioned to study neutrinos produced closer to home, in our atmosphere from cosmic rays. It helps us unravel this really interesting phenomenon called neutrino oscillations, where these particles can actually transform between different types as they travel.
It's like they're shape-shifting as they go through
Yeah.
space.
Yeah.
Okay, so we have RCA peering deep into the cosmos and ORCA studying these neutrinos closer to home, both using the Mediterranean Sea as their giant laboratory. But let's get back to that incredible discovery. Take us back to February 13th, 2023. What happened to KM3NET that day?
So imagine you're a scientist, you're looking at the data from RRCA, and suddenly one of the sensors lights up, signaling the detection of a muon particle with unprecedented energy. Muons are created when a neutrino interacts with matter, leaving a trail that we can trace back.
Like a breadcrumb trail, leading back to the source of the neutrino.
Exactly. And by analyzing the muon's path and its energy, they confirmed that it originated from a neutrino nearby. And the energy of that neutrino, well, it shattered all previous records.
220 PeV.
Yeah.
10 times the energy of the most powerful particle accelerator on Earth. That's incomprehensible.
It really is. And this isn't just a beta point, it changes how we understand the universe. It opens up all these possibilities for studying these processes happening out there.
So where did this neutrino come from? It's like a cosmic detective story.
That's the perfect way to think about it. And like any good detective story, we have a couple of suspects. One possibility involves what we call cosmic accelerators.
Make accelerators. What are those?
Imagine a gigantic particle accelerator in space, like a black hole,
Right.
at the heart of a galaxy, or a gamma ray burst, one of the most powerful explosions in the universe. These environments accelerate protons to almost the speed of light, smashing them into other particles, and creating a cascade of high-energy particles, including neutrinos.
So these accelerators are like giant slingshots, flinging neutrinos across the universe with mind-blowing energy.
Exactly, and that's just one possibility. The second one involves what we call cosmogenic neutrinos.
Cosmogenic neutrinos. They sound even more mysterious.
It's a little complex, but picture this. Ultra-high-energy cosmic rays, which are themselves supercharged particles, zipping through space, interact with the leftover radiation from the Big Bang. This afterglow from the beginning of the universe is still out there, and these collisions can produce neutrinos with extremely high energies.
So you're saying that the Big Bang's echo is playing a role in creating these neutrinos?
Exactly. And now the challenge is to gather more evidence, more clues, to figure out which of these scenarios is more likely.
This is getting really interesting. We have two possible origins: cosmic accelerators or interactions with the Big Bang's afterglow. It's a real mystery. I can't wait to hear more about how we might solve it.
Me too. And that's exactly what we'll talk about next. Okay, so we've narrowed down the potential suspects in our cosmic whodunit. Now the real detective work begins. So to determine which of these scenarios is, more likely, the cosmic accelerators or the interactions with the Big Bang's afterglow, well, we need to look for more clues. And those clues come in the form of additional neutrino observations.
Okay, so we're on a neutrino treasure hunt. But how do we get more clues from these ghost particles? They're so hard to detect.
It's all about analyzing the properties of the neutrinos we catch, their energy, their direction, even the type of neutrino. These all give us information about their origin and the events that created them.
Sounds like we're deciphering a secret message from the cosmos. So let's break it down. What can the energy of a neutrino tell us?
Okay, so think about this. If you see a rock skipping across a pond, you know it was thrown with a certain amount of force. The faster the rock, the stronger the throw, right?
Right.
So
Yeah.
the energy of a neutrino, it directly reflects the power of the event that created it. The higher the energy, the more extreme the source.
So finding a neutrino with an energy of 220 PeV tells us it must have come from something truly cataclysmic.
Exactly. And the direction a neutrino travels acts like a pointer, guiding us back to its source. It's like tracing the trajectory of an arrow back to the archer.
So by combining the energy and direction of multiple neutrinos, we can pinpoint the location of these events.
Yes. And there's one more clue. Hidden within each neutrino, its typer, or what we call its flavor.
Flavor.
There are three types of neutrinos: electroneutrinos, muon neutrinos, and tau neutrinos. And the ratio of these different flavors can help us distinguish between different astrophysical processes.
So different cosmic events produce different flavors of neutrinos. That's amazing. It's like each flavor carries a unique fingerprint.
Yeah, you got it. For example, if we detect a higher proportion of muon neutrinos, it might point towards certain types of cosmic accelerators, while a different mix could suggest interactions with the Big Bang's afterglow.
This is like a whole new language of the universe. It's incredible. But why are neutrinos so important? I mean, aside from helping us solve these cosmic mysteries, what makes these ghost particles so valuable?
Well, neutrinos offer a unique perspective on the universe because they interact so weakly with matter. They can travel through very dense regions of space, like the cores of galaxies or the remnants of supernova explosions, completely undisturbed, while light and other particles get absorbed or scattered.
So they're like tiny explorers, bringing us information from places that are otherwise hidden from view.
Yeah, exactly. They give us a glimpse into the most extreme environments in the universe, places we could never observe directly with, telescopes.
Okay.
And this is where neutrino astronomy really shines.
I'm trying to understand why scientists are so excited about these particles. It's like opening a new window into the cosmos.
Precisely. And KM3NET, with its ability to detect these high-energy neutrinos, it's at the forefront of this field. But there's still so much we don't know.
What are some of the big unanswered questions that neutrino astronomy is trying to address? What mysteries are we hoping to solve?
One of the biggest mysteries is the origin of cosmic rays. These very energetic particles that bombard Earth from space. We've known about them for over a century, but their source is still a puzzle.
You mentioned them earlier. They're like tiny cannonballs, carrying more energy than anything we can make on Earth.
That's right. And as we discussed, cosmic accelerators, those same events could also be responsible for these cosmic rays.
So by studying the neutrinos coming from these environments, we can learn more about the processes that are, launching these cosmic rays.
Yeah, exactly. And there's another question neutrinos might help us answer: the nature of dark matter.
Ah, dark matter. The invisible stuff that makes up most of the matter in the universe? We know it exists, but we still don't know what it is.
Right. And some theories suggest that dark matter particles could annihilate each other, producing a shower of particles, including neutrinos.
So by detecting these neutrino signals, we might finally be able to identify these dark matter particles.
It's a challenge, but the reward is huge. Unraveling the mystery of dark matter would change everything.
It's amazing to think that these tiny, almost invisible particles could be the key to such big discoveries. What other mysteries are neutrinos helping us to solve?
Well, they're also providing insights into supernova explosions, the births of black holes, even the evolution of galaxies over billions of years.
So it sounds like neutrino astronomy is really taking off. What does the future hold? What are the big goals for the next few years?
Well, one of the biggest goals is to just expand the size and sensitivity of neutrino telescopes, like KM3NET. The more neutrinos we can detect, the more data we have. The better we can understand these cosmic messengers. It's like building a bigger antenna, to listen to the whispers of the universe.
So we're basically casting a wider net, to
Mm.
catch more of these particles.
Yeah, exactly. And we also need to improve our ability to pinpoint the sources of these neutrinos with more and more precision. And this requires collaboration, not just between different neutrino telescopes, but also with other types of observatories, like telescopes that observe light, gravitational wave detectors, all sorts of things.
It's like putting together a giant puzzle where each piece is a different type of observation.
Yeah, that's a great way to put it. The era of multi-messenger astronomy is here, and neutrinos are a big part of it. By combining data from all these sources, we can create a richer picture of the universe.
It's amazing to think that this tiny single particle can tell us so much about the universe. This deep dive has been really amazing.
Yeah, it's been fun talking about it. And I hope you, the listener, are now just as fascinated by these neutrinos. They're not just a scientific curiosity, they're a fundamental part of the universe, carrying secrets that are just now being revealed.
Yeah, absolutely. I feel like this is just the beginning. Who knows what incredible discoveries are waiting for us?
Yeah, I agree. So keep looking up, keep asking questions, and, never underestimate the power of these tiny particles to help us learn about the cosmos.
Until next time, thanks for joining us on this deep dive. We'll see you on our next adventure into the wonders of the universe.